we propose HumanGPS geodesic preserving feature for dense human correspondences. Building correspondences is one of the most important problems in computer vision. In this work, we revisit this problem specifically for human body, where the goal is to build dense correspondences between human images and the different body poses, identities, and camera viewpoints. Such human correspondences are in high demand and can potentially impact many applications, such as multi-view reconstruction, non-rigid tracking, appearance transfer, and neural rendering. Previous works build dense correspondences between images, typically by extracting features from images, followed by nearest neighbor search or optical flow algorithms. However, most of them were designed for generic scenes without incorporating human-specific knowledge. Alternatively, with the human body as prior, correspondences can be obtained via sparse joint detection, parametric model fitting, directly regressing predefined UV coordinates, and between 3D shapes. However, the accuracy of the correspondences often suffer from the limited representation capability of the human prior model, so that the object boundaries and complex geometry, such as loose clothing and hair, are not well handled. We propose a deep learning method to build dense human correspondences, taking advantage of both non-prior and prior-based methods. The core of our method is a feature extractor that maps human pixels to normalized high-dimensional embeddings, which is trained with novel loss functions relying on 3D human surface to incorporate priors. Similar to previous methods, the distance in the learned embedding space can be used to build correspondences via nearest neighbor search or taken as important inputs to optical flow methods. Traditionally, triplet loss is commonly used to minimize the feature distance between matching pairs, and equally pushes apart the non-matching pixels, which does not discriminate between minor and major mismatches, and hence leads to non-smooth and ambiguous feature space. In contrast, we propose to learn a feature space in which the feature distance between pixels maintains the order as measured by the geodesic distance on the 3D human surface. That is, if BA is closer than CA as measured by the geodesic distance, the feature of pixel A should be closer to B compared to C. And we call this feature space the geodesic preserving feature. To learn this feature space, our novel loss functions consists of 4 terms. Consistency loss is to minimize the feature distance between ground truth corresponding pixels. Sparse ordinal geodesic loss is proposed to encourage the order between 2 target pixels with respect to the reference pixel in feature space to be the same as measured by geodesic distance on 3D surface. Because it's non-trivial to extend ordinal loss to all the pixels in an image, we relax the ordinal constraint and define dense geodesic loss between a reference pixel to all other pixels in the image. This loss does not explicitly penalize wrong orders, but pushes feature of all non-matching pixels apart with different force depending on geodesic distance to the reference pixel. Lastly, we extend dense geodesic loss to crossviews. To train our model, we created synthetic data from multiple 3D assets, including simple, rendered people, and the relatables. Image pairs are generated with large camera viewpoints and body pose variations. To evaluate the performance on intersubjects, we also produce intersubject testing data from simple. Our method outperforms all the state-of-art, and ablation study shows that all the loss terms matter to the performance. Qualitative results show our methods produce more precise and smoother correspondences compared to previous methods. What can GPS help for building dense correspondence? Here visualize the feature distance map of frame 2 with respect to a reference pixel in frame 1. Compared to the model trained by triplet loss, our model can capture the semantic information to tackle left-right ambiguity. Furthermore, GPS features can be used to build dense correspondences across different people, even without using any intersubject data during the training. While our model is trained on synthetic data only, it generalizes well on unseen real image in the wild. First, compared to dense pose, our method can handle persons in loose clothing, and the produced feature space is smoother and consistent across subjects. Secondly, GPS feature can provide an additional correspondence across different time steps for the non-rigid fusion, and improves the robustness for captures with fast motion, and benefits morphing to create a smoother animation between human images. Data code pre-trained models, demos, and this video with closed caption available on the project webpage. Thank you.